Hi everyone, my name is John Jackson. I'm a PhD student at CU Boulder, and today I'm excited to talk to you about control synthesis with local GP regression for offline-online control of autonomous systems. As autonomous systems become more capable and more complex, ensuring their behaviors in safety-critical environments is becoming very important. For example, we want this UAS to pick up this package, safely travel to its destination, and deliver it, all while respecting flight and payload restrictions and avoiding all other vehicles. My research makes this more difficult by considering the case of unmodeled or unknown dynamics, such as the case where this package with unknown contents is affecting the flight dynamics of this aircraft. I'll begin by modeling this as a discrete time stochastic system, where F is the known component of the dynamics, which might come from first principles modeling, and G captures everything we don't know, everything that we can't model beforehand, and higher order nonlinear terms. The process noise is sub-Gaussian, which captures the Gaussian distribution. This mission can be expressed as a linear temporal logic over finite traces, which has the same syntax as LTL, except it's interpreted over finite time. The goal is to find a strategy for this system to choose actions in order to satisfy phi with some performance guarantees. Instead of knowing G, we do know that we have a data set that's been generated by the system, and we also have the ability to collect more data in order to learn about G more. So the question is, how do we use these offline and online observations of G to synthesize a strategy that is going to maximize the chance of satisfying the specification? Our solution to this problem consists of combining tools from formal control synthesis, which can provide guarantees on models with respect to mission specifications, and machine learning regression, which can learn models from data, but not necessarily with strong guarantees. We start with the given system data in an LTL-F specification and do offline control synthesis. This framework, which I presented earlier this year at HSCC, uses GP regression and finite state abstraction in order to come up with an offline control strategy. This strategy has guarantees on satisfying the mission specification that apply to the underlying system. In this work, I extend this offline approach with an online loop that lets me reason over the abstraction, choose better actions, and perform local regression updates in order to refine the abstractions. I'm first going to begin with an overview of this offline component. The basis of our approach is Gaussian process regression, which we use to learn the unknown components of the dynamics. We do this in order to quantify the error between what we learn from data and the true underlying model. The caveat is the process noise we're using may not be Gaussian, which breaks some assumptions about vanilla GP regression. In order to overcome this, we use error analysis tools from the reproducing kernel Hilbert space field of literature in order to find sound probabilistic model errors. We use this as a basis to construct an abstraction of the system in the form of a product interval Markov decision process. This abstraction captures all system behaviors with respect to our specification phi. Notably, sync states in the abstraction correspond to violating the specification. Accepting states correspond to satisfying the specification or completing the mission. The intervals that dictate how the transitions between states occur capture the learning uncertainty, which comes straight from GP regression, the stochasticity of the dynamics, and the discretization error realized when we construct these finite states from the continuous state space. This product IMDP can be used to define a measure of success in reaching the accepting state. We can't directly calculate the probability because we're working with interval probabilities, but we can define the lower bound probability of reaching this state. The offline strategy, pi, that we want to synthesize aims to maximize this lower bound value function, which defines the minimum probability of satisfying phi from each state S. This boils down to playing a 2.5 player game on this abstraction, and we show that if we construct this soundly, this strategy and the guarantees, or these lower bound probabilities, map back to the underlying system. Now, the problem crops up when the uncertainty is high. For example, when we don't have enough data, this lower bound can be 0, meaning we can't provide strong guarantees on satisfying the mission. So the question becomes, how can we refine this offline strategy using data that we collect online to increase this chance of satisfying phi and completing the mission? This brings us to the online component of our framework, where we extend these abstraction and strategies into the online setting by first reasoning over the abstraction, choosing the next best action, and finally using new data to update our regression and the abstractions, closing the loop. So I'll next give a high-level overview of each of these online steps. The first step of the online component is to reason about the abstraction by using the current state of the system. Suppose the current state is in the abstraction state SK. We automatically know the possible future states that the system may transition to based on the abstraction. We then use this state to augment the PIMDP by introducing the state S tilde. We can reason about this single point and identify tighter transitions in the abstraction and get a better sense of how the system is going to evolve. We then calculate the lower bound value function from this new augmented state, which is straightforward to do, as these lower bound values at successive states are already calculated offline and they're unchanged for the original IMDP states. As such, we see monotonic increase in this lower bound value function, which guarantees that we can always at least do as well as the offline policy. We use this as a basis to choose the next best action. Ideally, we'd like to choose an action that always maximizes this lower bound value function. And if it goes to 1, we're sure to satisfy phi. But oftentimes we get ties in this function, such as having a 0 lower bound for every action. As such, we have to introduce metrics to break this tie and make progress towards completing the mission. The first heuristic we introduce is one that avoids sync states in the abstraction. If we reach a sync state, we violate the specification. So we choose actions to minimize the chance of reaching one of these sync states over the next step. This can lead to preferring safety over making progress, so we introduce the next metric, which is making progress on the PIMDP by looking at the expected number of edges to an accepting state. And we choose the action to minimize this value. As such, we combine this metric with the sync state metric in order to make progress in satisfying the specification. Once an action is chosen and we execute it, we get new data that we can use to update our unknown dynamics regression and update our abstractions. Using all of the data to update our regression results in the best predictive variance that we can get, but it's very expensive, as vanilla GP regression is ON cubed with the size of the data set, and it makes it very expensive to reason about online. Instead, we turn to using local Gaussian process regression, where we use the n nearest data points around the data that we've collected in order to update our regression and abstractions. This lets us reason faster and enables online learning, but it does increase the predictive variance and uncertainty. So it is a balancing act between these two objectives. Once we have the GP, we can finally update our abstraction by identifying those states around the new data that we've just collected and trying to improve the transition intervals between each one of these states. And as we collect more data, we can expect some intervals to disappear completely as our abstraction starts to represent the true transition dynamics even more. That's the online extension to our offline synthesis algorithm in a nutshell. And as I mentioned previously, we're guaranteed to at least do as well as this offline strategy, but empirically, we observe big improvements in closing this loop. The example is a 2-dimensional system with 4 a priori unknown control modes that moves the system in the north, south, east, and west directions with nonlinear sine and cosine terms that couple the states. The mission is to go from A to B in any order and always avoid these regions O. I performed offline abstraction synthesis with 200 data points for each one of these control modes. And online, I used local GPs that considered the 75 nearest data points. This illustrates simulation results using the online control loop at 3 different initial conditions. Here, the system goes from B to A and satisfies the specification. Here, it goes from A to B and satisfies it. But in this corner, the system initialized at A is not able to reach the region B. For a more quantitative view on these results, I performed 500 simulations at each one of these initial conditions. I compared the result of the offline policy alone to the online loop considering different GP setups, a GP using all the data without updating, a GP using only local data without updating, and then the GP using only local data but considering new data it collects on the way. We can see that using the control loop online results in big improvements in the percent of satisfying runs, no matter which GP scheme we use. But using local updates sees the biggest increase in the percent of satisfying runs, close to 100%. In the more challenging corner here, the offline policy results in 65% satisfying runs. The online control loop sees decreases in the percent of violating runs, but only using local GPs with new data do we see an increase in the percentage of satisfying runs from 65% to 86%. And the number of violating runs decreases to 10%. This concludes my overview of our synergistic offline and online framework for synthesizing safe controllers for systems with unknown dynamics. There's a lot of exciting extensions of this work, including extending theoretical guarantees of convergence for cases such as this one, augmenting this abstraction-based approach with abstraction-free approaches such as control barrier functions, and identifying and testing autonomous systems applications where this kind of approach will really shine. Thank you so much for listening.